Awesome. Thank you so much for the introduction. I'm excited to be here. Carl's talk was fantastic, by the way. So we're going to talk about high-performance serverless with Rust. If you've come and are familiar with Rust or are just getting started or been doing it for a while, you know that Rust is lauded for being highly performant. It's extremely safe. Rust is known for being able to build applications that have fewer bugs, fewer defects. It's got a solid developer experience. And pairing it with serverless is not necessarily something that you would normally think of. Rust is often thought of as a systems programming language, something that's networking, traffic routing, storage, those sorts of scenarios. But what I want to talk to you about is how we can pair it with AWS's serverless, and specifically Lambda, and to bring together a really nice, performant, pay-as-you-go, no infrastructure to manage solution that's deeply integrated with other cloud services. As Daniela mentioned, I don't come from a systems engineering background. I've been doing Rust off and on for about a year, but I've got about 8 or 9 years with AWS Lambda, which, by the way, just turned 10 years old recently. And so I was extremely curious about coming from a different background and how I could start working with Rust. Sorry. So real quickly, just real briefly, who am I? So I've been doing this for quite a while, 25 years in technology. So I remember the dot-com days. I've been everything from a developer all the way up through a CTO. So I've got a bunch of different roles in my background. I'm a big believer in serverless first, hence the talk, right? And serverless is more than just compute, and we'll talk about that in a second. I'm also a big fan of things that are compiled, also talking about Rust. I'm an AWS community builder, so it's a global network that's sponsored by AWS that focuses on evangelizing and talking and writing about their technology. And as Daniela mentioned, I'm co-founder of a company with my wife who serve and help customers with AWS and cloud technologies. Those are my socials, but I'll give you a link at the end that you can get to. So before we get started, I want to have some serverless ground rules. So forget what you've read on the internet. There's lots of different descriptions about what this might be. For the balance of this talk, when I mention serverless, these are the things that I want you to be thinking about. Serverless by nature, again, in my opinion, has nothing to provision and nothing to manage. And what I mean by that is that I don't have to worry about standing up virtual machines. I don't have to worry about things being available for me at any point in time. I don't have to worry about, do I need to update or patch or manage an underlying environment? With serverless, things will scale predictably with usage in terms of cost. So for every event that I handle in serverless, every payload that I process, every CPU cycle that I burn, I'm going to be paying for that. On the contra of that, anytime I'm not doing those things, I'm also not paying for that usage. So contra that with something that's always on, serverless is more always available. However, you also don't have to deal with planned downtime. If I've got an application that's written and hosted by AWS's Lambda, I'm not going to go ahead and tell my customers, hey, on Saturday from 3 to 5 p.m., Amazon's going to update Lambda, therefore you can't use this during that time. That isn't the case with serverless. There is no planned downtime. And one of the really sticking points that I like to mention about it is it's ready to be used with a single API call. A lot of times when working with services in the cloud, you'll go hit the button, start, you'll wait 10 minutes, only to find out your service is now ready. With Lambda, this is as simple as dropping some code in the environment, giving an event, it's up and running. I'm not waiting. So these are some things I want you to be thinking about as we dive through the rest of the talk. So as I mentioned, I'm a year into my Rust journey, but about 8 years into using Lambda at all different scales, right? Everything from hobby projects all the way up to hundreds of thousands of concurrent users that are running against the systems. So first and foremost, these are some tips, and 3 of them, that I think are extremely important as you get started working with Rust and working with Lambda. And at the tail end of this, we'll get into why I believe that it's the high-performance choice. So first up, we're going to look at creating a multi-lambda project with Cargo, why we do that, what that supports. We're going to look at using the AWS Lambda runtime and the SDK that's associated with it. And then we'll talk real briefly about repeatability and infrastructure as code. So first up, creating a multi-lambda project with Cargo, I want to walk through the way that I like to think about organizing my application, and very specifically an API, as we're going to go throughout the rest of the talk. So there's a couple of different thoughts here. If you've done any, have any experience with Lambda or have read anything about using Lambda for APIs, in a lot of cases, people will talk about these things called Lambda lists versus a Lambda per verb. So at its fundamental level, you can think of Lambda as a micro nano compute service. You might have this microservice, right, which is composed of multiple gets, multiple puts, posts, deletes, an entire route tree that might support your REST API. My preferred approach with working with Rust is to build out one Lambda per each verb and each route that I'm going to support. So if you're familiar with something like Axum or Warp, right, you may have a route tree that's exposed over there. We're going to talk about how to expose routes over individual Lambda functions. And then just to kind of round out the rest of the project, but we're not going to dig too much into it, is I also like to deal with change individually in a Lambda as well. And we'll do this for a couple of reasons. First and foremost, if you were at the keynote this morning, Kawaja talked about blast radius and talked about de-risking as you're getting into a new project. By carving up my Lambda functions into these nano services, essentially, I'm de-risking my changes. I'm de-risking my runtime. For instance, let's say that I've got a get Lambda that is performing a query on a DynamoDB table, and I've got a defect in that get Lambda. My put, post, delete, patch, whatever could be completely isolated from that get. Therefore, I can just update that get function without disturbing any of the rest of my ecosystem. So I've kind of firewalled off, so to speak, my changes to protect myself as I work through the project. However, that does tend to create a little bit of isolation, right? Which then can cause some challenges when thinking about code reuse. This is an example of a typical project that I've got that I want to work through. The code will be available at the end of the talk. There's a link out to it so you can clone it and work with it. It's in GitHub. I didn't want to tempt the demo gods this morning. So the way I like to organize this project is structured in two halves, right? Up at the very top, you've got this infra directory, which is where my infrastructure as code is going to be, which we'll talk through at the tail end. And then I like to organize all of my functions up under this lambdas directory. And if you notice, I've got each of the individual operations or routes that are exposed underneath those folders. So I've got delete by ID, I've got a get all, I've got a put, and I've got a post. Each of those projects are essentially Rust binaries. When we get to the third section, we talk about infrastructure as code. It's going to compile each of these down to their own individual binaries for execution inside Lambda. And then at the very bottom, I've got a shared library, which we'll talk about. So it's just a shared directory, and we're going to look at how we can organize our code to be able to be reused across those projects. So one thing I kind of want to demystify a little bit is that Lambda in working with Rust isn't really any different from working with other Rust projects. This is a multi-project setup. I can take advantage of cargo and workspaces so that I'm able to organize and reference my code across these different Lambdas. So as you can see, I've got the same 5 Lambda: post, get, delete, put, and get all. And they're going to be able to access that shared Lambda project. And why do I want to do this? So thinking about how to access code, if you're familiar at all with Lambda, there's a concept of layers in Lambda. And layer Lambdas are super useful for TypeScript. They're useful for Python. They're useful for languages that can bring in binary or bring in references kind of on demand. We don't have that dependency, so to speak, with Rust, right? So things are going to get compiled in. So what I like to do is I like to organize all of the different things that I'm going to need for my application that might be reused across those different Lambda operations. We'll talk a little deeper about AWS client building, but I also like to organize my entity models. So if I've got domain objects or I've got operations that might be core to my business, I might put this in my shared library. If I've got data transfer objects for my API that might be reusable across any of those functions or across those operations, I put them there. And then if I've got any common error structs, right, that I may want to treat errors and failures the same across my boundaries, I can put that in that location. And so again, just to kind of show that there really isn't anything special about pairing these two together, building a shared library that works with Lambda is the same that you would with any other Rust project. It's just marked as a lib or a library. We include our required dependencies, and we've got our shared package details that are required for that project. So next up, I want to drill into a little bit about using the Lambda runtime and SDK. So working with Lambda is a little bit different than working with maybe a traditional container-based application. And I want to make something kind of clear right now. So the AWS Lambda runtime for Rust is different from what you might be familiar with from the runtime if you go to the AWS platform. So if you were to go to AWS Lambda right now and want to go build a new Lambda function, Amazon is going to ask you which runtime would you like to use. And they're going to list TypeScript, they're going to list Ruby, they're going to list Python, they're going to list .NET, it's going to have Java, and you're not going to see a runtime for Rust. The reason is that the runtime that AWS is talking about is the runtime that your language requires in order to execute your code. As you all know, Rust is not dependent upon a runtime. Therefore, you're going to select one of the Amazon Linux containers or the Amazon Linux runtime. However, there is this notion of a Rust runtime, which we're going to talk about. And it's extremely important because Lambda at its core is nothing more than a service. Its job is to handle events that are passed into it, whether that's a queue, a stream, a web event, and it's going to communicate with your code over this runtime API. It also exposes an extensions and telemetry API, which is not super important for this discussion, but the runtime API is very important because it is going to handle what event comes in, it's going to forward it onto your function. Your function is then going to deal with that event that came into it. It's going to process, do its logic, and then it's going to return back out to the Lambda service so that the Lambda service can then do whatever it was going to go do upstream. And so why the Lambda runtime is important, because it is an open source project, and what its job is to do is it's going to communicate back and forth with that Lambda runtime API in order to serialize and deserialize payloads for you. It's going to basically send an event loop to deal with those changes that are coming in on your behalf. And then you're going to be able to just focus on writing your function code, which we'll look at in a second. Now, you might be wondering, what kind of overhead does something like this produce? Not nearly enough that you should go out and try to build this on your own. Well, I'm not going to go out and build this on my own. So the amount of overhead that's involved here is nominal, and I'll show a little more about that in the performance section. But it simplifies your life significantly because, like I mentioned, it's able to communicate back and forth with the Lambda API. It does contain multiple projects inside of it. So it's got provisions for dealing with an HTTP superset, which is what I'll show in the examples. It is capable of working with the extensions API. And very importantly, it's got an events package that's inside of it. So anytime you work with a different service in AWS, the payloads are going to be different as they come in. So an SQS payload is going to be different from a API gateway request payload, which is going to be different from a S3 payload, and on and on and on and on. This library has provisions for us to be able to work with those out of the box, which, again, you could do yourself, but why if it's already done for you? So to drive in just a little bit about what a function or about what a Lambda function looks like, and I want to really show you how simple some of this is, because the thing I love about writing Lambdas is that I don't really feel like if I make a mistake, I can't unroll it pretty quickly. A lot of times I'm writing 100, 150, 200 lines of code to provide an operation. My brain can reason about 200 lines of code. Sometimes you open a large project and there's 15 routes or 20 routes or whatever it is. It's a lot to kind of think about and get your head around conceptually. Lambda to me feels like the nice bite-sized chunk of code for me to be able to work with. So the function is asynchronous main, which is enabled by Tokio. Which was great to hear that talked about a little bit this morning. As my main runs, it's a regular Rust binary, like I mentioned before. I'm going to do things in main to initialize things that I want to be able to reuse down the line. I'll get into this in a little bit about talking about performance, but what's interesting is they're online, right there where the cursor is, initializing shared clients and being able to reuse those on subsequent operations save me the time of having to stand up dependencies ahead of time, or at execution time. Because main will get run once, I will get dinged for that setup, and then every time my function handles an event, I won't have to do this again. Right? So if I'm saving myself 100 milliseconds, I do it up front. I never have to pay that cost again. Because when we look at the anatomy of a simple handler function, this is my get operation right here. And what it does is, it's going to be querying DynamoDB. It's going to be handling a specific response. And then it's going to be sending that response back out to the Lambda service, which is going to go on to wherever it was supposed to go. So as I mentioned, this code right here gets executed every time. It's going to happen on the first call, and it's going to happen on the millionth call. But my main is only going to get executed just that one time. So I want to do my best to make sure that I set up what I want to so that I can benefit from reuse inside of my subsequent requests. So second half of tip 2 is the AWS SDK for Rust. Everyone in here, I'm sure, knows what an SDK is. I'm not going to go through the nitty-gritty of what that is, but I do want to highlight why I believe if you're starting a journey or getting into writing Lambdas and serverless compute with Rust, I think the SDK is important. There's some nuggets inside of here that I think nullify, especially if I'm using something like DynamoDB. I don't worry so much about data access because that's taken care of with the SDK, which we'll look at. So I mentioned that Lambda and Rust, I've got a really rich ecosystem to work with. So being in AWS means that I can get a whole lot of other capabilities simply by connecting to that service. Some of these that are listed up here are serverless, right? Amazon SQS, AWS Fargate. Some of them, there's Lambda again, S3, and then others may not be as serverless. But the AWS SDK for Rust is going to give me access to be able to connect and communicate with any of the different AWS services that I want to. And so in order to do that, I want to think about the fact that the SDK wraps, like I mentioned, each one of those individual services. Why is this important? Well, again, I go back to my blast radius. If I have a get operation that is a Lambda function that only works with DynamoDB, guess what? I'm only going to pull in the DynamoDB client. If my post operation needs to write to DynamoDB and then also send a message on EventBridge to put a message on their bus, I'll bring that in. So as I build these functions, I can specifically carve out what it is that I need to be able to do to support that function. On the addition of that, if you're thinking about security, the AWS SDK for Rust deals with identity and access management for you. So if you've got familiarity with AWS, you know that identity and access management is very important. Every service has its own set of permissions that it's listed for. If I want to execute a GET with Dynamo, I either need to grant star, which is a really bad idea, or I just want to grant GET item. Or if I want to work with an index, I might want to give it permissions to get and access that index. So by being really fine-grained again with my Lambda functions, being very specific about the things I'm pulling from the SDK, I'm going to get this nice, tight, really well-secured block of code that's going to do just what I want it to. And then lastly, since it is a web service, Amazon Web Services, you'll have these nicely defined structs for dealing with request and response. So I want to highlight just real quickly, I'm going to spend, like I said, tons of time talking about SDKs. But a DynamoDB client, every one of the clients that I've worked with, from SQS to S3 to DynamoDB, they all have a similar shape and structure to them. You're going to specify the region or the provider, and again, if you're using this in your environment, it's going to have local credentials. If you're using it out in the cloud, it's going to have a service account for that Lambda to be able to operate with. What's really nice is that if you are doing any kind of local development, which I like local development even though I love cloud development, you can specify local endpoints like I'm doing right there to be able to access local services. And this client becomes your gateway into all of the API operations that you're going to use throughout the life cycle of your Lambda function. And what might those operations be? So like I mentioned, for Dynamo, it's going to be get. You're going to have puts. You'll have deletes. And then they'll usually support batching of operations should you want to. What I really like is that I can go read the API specification, and the Rust SDK for AWS looks very much like that AWS API specification. So just to kind of wrap this one up, this section, make use of the tools available. I would not recommend, especially if you're new to Rust and new to AWS, you trying to write your own AWS runtime for Lambda. He worked for AWS. I'm not sure if he's still there, but big part of what's there, they spent a lot of time making that work. And then the AWS SDK for Rust is going to give you consistency, durability, and acceleration as you're building. Again, there's lots of customers in production that are already using this. Why try to reinvent the wheel? And the fact that you can feature flag and only toggle on what you want in your cargo file makes your ability to really kind of fine-grain what you're pulling in your builds. So the last piece of these 3 tips is I want to talk to you about repeatability with IAC. So infrastructure as code. So if you're new to the cloud or even been in the cloud for quite some time, you may not have heard of infrastructure as code. But if you're familiar with it, this is why I think it's super useful, and I want to talk to you about how to use it with AWS and Rust. So infrastructure as code is a way to be able to build your infrastructure or build your services that you're going to use in AWS in a programming language of your choice, or a markup language of your choice if you want to. And so by being able to do that, it's going to give me repeatability, right? I don't have to remember the 7 steps I click to make it work when I go to QA or when I go to production. I've got code that I can execute and run over and over. It may seem like a pain to get started, but you're going to have repeatability. Speed as things increase. So as I pull more services in, I'm going to be able to share this with my developers. So the last thing as a developer that I want to do is be dependent to infrastructure. I want to be able to move at my own pace. I'm not saying you shouldn't move with infrastructure. I'm saying that by being able to write my own infrastructure declarations and code helps me move faster. It also builds more buy-in as you get up to the cloud and as you start running load. And then it's a great foundation for that partnership with infrastructure for automation. So as you start to build continuous deployment, your IAC becomes extremely critical. So there's a lot of choices in the serverless landscape. My kid's favorite is Sam the Squirrel, for obvious reasons. That's the serverless application model. That one has the best logo. Terraform, it's an AWS product, by the way. It supports YAML and is fantastic. Terraform is another one, which is a popular provider. The bottom left is the serverless framework. So if you spent time in the serverless space, they've been around for quite some time. And there's Pulumi down there on the bottom right. There are others. These are just the 4 competitors that I often see. I'm a proponent of the Cloud Development Kit by AWS, the CDK. I'm not a huge fan of writing a ton of YAML for this stuff. So with CDK, we can build it with TypeScript. We can build it with other languages should we want to. You can't yet build it with Rust, which is kind of a drawback. But so how do I embed a cargo build system or a cargo patterns, right, with CDK? Well, first off, there's another really great open source project called Cargo Lambda. Cargo Lambda is a subcommand for Cargo, which will help you do builds, does cross compiles. I believe it's supported by Zig. Release optimization, right? Stripping of symbols, minification where it can, things of that nature. Local development support, which we'll talk about here in a second, which I think is fantastic because, again, you always want to push your code to the cloud to be able to test. It will leverage Docker or your local build environment, which is great. So if I'm trying to support ARM and I'm only on an x86, I get my local builds happening that way. Or if I'm going out to a build system in the cloud that doesn't support it, it'll be able to do that as well. And then we'll easily be able to embed it to support automation in our build pipeline. But how do I embed it with my chosen CDK? Well, again, there is open source project for this that is an extension of the Cloud Development Kit. Just real briefly, the Cloud Development Kit supports 3 levels of abstractions. Level 1 is basically raw bare metal CloudFormation. Level 2, which is about what this is, it's going to be essentially one service wrapped in an abstraction for you. And then level 3, you're like compounding multiple different services together all in one package. If I wanted to put together a Lambda plus a DynamoDB table plus an API gateway plus an SQS, that would be a level 3. So this Cargo Lambda library will support my REST function. This is TypeScript. I give it a function name. I give it a manifest path, which is simply the directory that's going to point to the TOML file for that library. So again, if I had 5 functions, I'm going to have 5 of these things. Memory size with Lambda, and I'll show you here in a little bit. Memory makes an impact on cost, compute, performance. Architecture can be ARM, which is Amazon's Graviton, or I could have done x86. And then any environments that I want to pass in, right? So environment variables that my function might need to be able to support its operation. So I mentioned local testing. Cargo Lambda supports local testing by allowing you to pass elements that look like the events that your function is going to work with. So the very first one is invocation of my Lambda. If I only have one Lambda in my project, I can invoke my Lambda with that payload for foo.bar if that's what my event looks like. If I've got a multi-Lambda project, like we've been talking about, I can specify, invoke, and then give it the name of the Lambda that is going to go back actually to the project binary name that I gave it. But foo.bar is great, but what if I had like this really complex payload, right? I can also then pass in a data file. As a Lambda developer, as targeting Lambda for compute, you're going to end up with collections of different payloads, right? Because I want to test a good payload, a bad payload, all these different combinations. Again, this can be part of like an integration test. It can be part of your build pipeline. It could also just be part of your local development as you get your arms around what's going on. And lastly, maybe you don't know what your payload looks like, which is totally fine. The Cargo Lambda project has got a set of API example payloads. So all the different event structures that I mentioned inside of the Lambda runtime project are also going to be available. The team that supports this provides all those payloads for you to be able to test with. So I mentioned Cargo Lambda, I mentioned CDK. We get a build. What does that look like? So CDK is going to, because of that Rust function that I defined, is going to drop out, run the cargo build. It's going to run Cargo Lambda build, and then it's going to generate a couple of things for me. CDK is going to do one part, and then Cargo Lambda is going to do the other part. First thing is the bottom example. That is essentially the CloudFormation JSON that gets executed. So all infrastructure changes in AWS happen through CloudFormation. For all intents and purposes. In this case, an automation is going to happen through CloudFormation. And so CDK is going to generate all of the different settings that I put together in my Lambda function. So if I specified 256 megs of memory, and I want to be on ARM, and I want these environment variables, and I want these permissions and these policies, that's going to all get emitted for me in this file that will get executed. The second part, which is the Cargo Lambda part, is that it's actually going to generate, in our case, we have 5 Lambda functions. It's going to generate 5 different packages, which are zip files that are going to be stored out in that directory. If you notice in there, if you can see that, which sorry for the small size, you're going to see an entry or a handler called Bootstrap. that's actually the name of the executable that gets generated inside of the zip file. That is changeable, but there's no real reason to change it because they're all isolated. So as you can see, by kind of pairing Cargo Lambda with my Lambda project, I get this nice clean isolation. I'm going to only get what I want that's changed. Lambda is not going to update things that I haven't mutated, and I also don't have to deal with the generation of all this cloud formation as I go up to the environment. So automation and repeatability are key, like I mentioned. I really believe that by investing in IAC up front, you're going to go faster as you get bigger, right? So maybe it's not a big deal for one function, and you're just testing, right? But you start to build real projects. You start to get 10 lambdas, 12 lambdas, 14 lambdas in a project. This automation is going to pay dividends because you're going to have other resources involved in it. Your Lambda is going to need DynamoDB, it's going to need S3, it's going to need SQS, it's going to need all of these other services that it's going to want to connect to. And by using this, Cargo Lambda gives me access to local deployment. It gives me that cross-compilation, which is fantastic. And then I get release-ready output. So just to kind of recap, what did we talk about so far? So 3 keys to success. Create a multi-lambda project with Cargo. I'm kind of prescriptive about it, but at the same time, I really struggled with this as I started to get going with Lambda and with Rust. Just how do I organize it? Do I put everything in one big monolith? Do I break them up? I found from a year of working with it and then from experience with Lambda, I prefer the isolation of one route, one verb per Lambda operation. You will spread out quite a bit, but again, I go back to the fact that so many things I won't change very often. So a lot of times you have stuff that you're not even going to visit. And things that are active development. I really prefer that isolation. Use the AWS Lambda runtime and SDK. Again, you don't want to deal with Serde and deserializing the different payloads in and out of your functions. Take advantage of that project that's out there. I know from experience and have seen customers run really nice size load with Lambda and with Rust that are using this project as an intermediary. And take advantage of the SDK. Don't try to write your own wrappers around AWS services. And the piece that most people skip over, the infrastructure as code, Cargo Lambda makes it so simple to get started early that there almost really isn't any reason why not to, because it's going to pay you off so many dividends. So I've talked for about 25, 30 minutes about this project orientation, infrastructure as code, but the talk was about high performance serverless with Rust. So I want to talk right here at the end and leave you with some things. Rust, to me, is the only high-performance Lambda choice. It's a pretty bold statement. I've run Go, I've run Java, I've run .NET, I've run TypeScript. I've not run Ruby or Python, but I don't believe they're any faster, just anecdotally, and we'll have some data here in a second. So Lambda really is, if you're looking to squeeze the most out of your compute, your usage, your price, Rust is the way to go. So why is that? How do you measure performance? Okay, so we're going to talk a little about 2 things that are kind of controversial in the serverless world. So we're going to talk about cold starts and warm starts. If you read about cold starts on the internet, they happen 80% of the time. They're the worst thing ever, and Lambda can't be used because it's got this cold start problem. Cold starts per AWS's research happen less than 5% of the time. Most of the common runtimes are extremely adept at being able to deal with them. I'm going to show you how Rust just skips over them. So the way Lambda works is you check in your zip, your binary, your package, goes up and it goes into the Lambda repository. I'm going to simplify this quite a bit, so I'm not going to get into too many of the nuts and bolts. So your code is sitting there waiting for execution. It's just hanging out. You're not getting charged. Again, remember, serverless, you only pay for what you use. I'm not paying for this zip file to sit in Amazon storage, by the way. The very first execution you get, that Lambda runtime is going to grab your code, it's going to pull it down, it's going to put it in the runtime, it's going to run your main function, it's going to do whatever initialization it has to do. The internet calls this, and AWS too as well, calls it a cold start. Starting from nothing, essentially. It's like starting your car on a cold day. I'm from Texas. We don't get many cold days, but I hear when you start your car on a cold day that it takes it a little while to warm up. Subsequent executions everything happens the same except for all the initialization stuff. Your function's warm. It's sitting in the environment. All it's going to do is run that handler code, and you're going to get what's called a warm start. Up until a couple of years ago, there's a significant gap, right, in the duration here. This could be multiple seconds, up to 10 seconds in some cases, for this to happen. Most of the common modern languages are now down to second and a half, less than 2 seconds. Think of an API, though. Like, if 5% of the requests, out of 100 requests, 5 of my users might wait a second for that first container to come up and go. And so the way Lambda works, too, is that I don't just get one instance. I'm going to get maybe hundreds of instances of my function running. So for every first time that 100th of instance runs, I'm going to get a cold start. And we really don't know how long warm containers last. Around 15 minutes of inactivity is about the rule of thumb, but that's not really documented anywhere. So let me show you why Rust is the way to go here. So this is an open source project that essentially what it does is every morning it runs a step function, which is another really cool serverless service by AWS. And I'll have the link at the end where you can go check it out. Written by an AWS engineer who used to be a Datadog engineer. And what it does is it runs this hello world, and then it checks the cold start duration, warm start duration, so a little snowflake and the lightning bolt, and then the memory used. So left to right, top to bottom, the most performant language from a cold start standpoint is C++ 11 on provided Amazon Linux 12. 10.6 milliseconds. Rust on AL2023 is right there at 11.27, but actually faster than C++ 11 on Amazon Linux 2023. It's at 11.27 milliseconds, 13 megs of memory, and 1.61 milliseconds on a warm start. Let's contrast that, because I'm going to do that here in a minute, on Node. Node's down here, way down here in the bottom right. 141 milliseconds. This is a hello world. This is just like the simplest of the simple. It's almost 14 times on cold start. It's almost 4 or 5 times on memory. And it's close to 13 times, 12 times on warm start. It's a significant difference in the performance on that. And so, okay, simple, hello world. I've got some graphics here. So there's an example that I ran that's based off that repository. It's running 100 concurrent users. Again, the load profiles as you go up pretty much the same. But what's interesting about this is that this is that DynamoDB operation. So that top graph is cold starts. That's executing, it's loading the environment, that's checking the IAM credentials, that's executing a DynamoDB query, and then it's coming back with a result that's coming through. At a cold start, somewhere between 100 and 150 milliseconds. So imagine that if I got on a cold start, 13 or 14 time performance difference. Think about how that extrapolates out to other languages. Again, 5% of my users. But if 5% of my users get 100 milliseconds, 150 milliseconds, or they get a second, if it's an asynchronous operation, nobody probably pays attention. But if I'm waiting on something to happen in a UI, I don't know about you, but if my bank takes more than a second, I'm pretty hacked off. Right? Like, I'm like, what in the world? I'm hitting refresh. So then go down, and everything kind of gets a little bit more insane as you go lower. The average latency is really sitting at around 15 milliseconds, and min latency is less than 10 milliseconds. Again, less than 10 milliseconds, execute a DynamoDB query, serialize, deserialize, then back all the way out. It's pretty crazy. So if you've been around the Rust ecosystem for a little while, you've probably seen this graph. I know that it was big at AWS reInvent last year. It's basically a graph of different languages and their energy and usage consumption and how they stack up. Again, Rust is always up at the very top. There it is. And the middle graph is like the total, some factor that's just greater than C, just a little bit greater than C. There's Go at almost 3 times. We get all the way down here to Ruby, TypeScript. That's like, again, 46 times. And from an efficiency and a total computation standpoint. So Rust built Lambda functions are just going to be naturally faster. And they're going to be naturally faster on an order of magnitude that's significant in some cases for your user base. And if user performance wasn't enough, and if we go back to my beginning statement on the serverless categorization that cost and usage are very closely linked, the argument's been made that cost, usage, and sustainability is also extremely linked. I'll leave you with this last slide just to kind of illustrate exactly why Rust is that choice if you're looking for high performance. So Lambda compute or Lambda pricing is basically done like this. Go out and there's a calculator that'll show you, but I'm going to simplify the math. It's basically your total compute times the memory allocated. So I mentioned earlier that you can specify memory when your Lambda function. Memory can be, I think, at 128 megabytes all the way up to like 1024. I mean, just a large number. And you can go up in 1 meg increments. And its CPU usage correlates and tracks with memory usage, even though you can't set it. Right? So the duration that's happening for the memory that I've allocated is going to equal my total cost. It's a pretty simple formula, but you can think of it as how long it ran and how much resource did I allocate is going to track back to cost. So broken down at really, really granular sense there, 1 millisecond, 128 megs, I'm not going to try to read it out, costs that top number. 128 milliseconds at 512 megs will cost that number. The reason why that 512 number matters is, first of all, Rust is not going to need 512 megs of RAM to run itself. I found its sweet spot to be between 128 and 256. Come find me later. I'll be happy to have that dialogue. It's a really fun calculator about how to look into that. However, other runtimes, and I use the runtime as in the runtime like TypeScript, .NET, Java, are going to require more memory. So I'm going to contrast TypeScript, which runs better with more memory than Rust. At a simple 1 request a second, this is just constant throughout the month. 1 megasecond at 128 megs of RAM is going to cost me 60 cents. Rust is going to cost me a penny, right, for a difference of 60.
Second or millisecond?
Cents, pennies.
So a second or a millisecond?
1 request per second. Just if you just got consistent traffic coming in from the internet or from an API call.
The calculation above is for a millisecond.
Yeah, that's the way the cost is.
Oh.
Yeah, cost. And so at 512, that number gets significant if $2 is significant and 3 cents is significant. At 100 requests a second, so again, steady stream of 100 requests per second for an entire month, my TypeScript function is going to cost me $61 versus $245 for 512. My Rust function still costs me $3 at max, which I'm not going to run it at max. I'm going to run it probably at 128. So I'm really almost comparing 245 against 86 cents. But 100 requests a second, I've got some Lambda functions that at some peaks may run 5,000 or 10,000 requests a second. But just to look at it at 1,000, TypeScript's going to cost me at 512 $2,400 a month. Again, if I've got functions carved up in a way that I have gets, puts, posts, deletes, I could have like a $15,000 bill to run TypeScript if I had any kind of traffic. But at Rust, I could have $40, $50. Because the argument's always made with Lambda, well, Lambda costs more, Lambda's expensive, Lambda's this, Lambda's that. The other thing about Lambda, though, is I don't have to pay for EC2. I'm not paying in for people to manage containers and networking. I have a lot of simplification. So if nothing else, my argument for Rust is that I can stave off the need for a container, except for some really high demand scenarios if I'm building APIs. And I can do that because I'm not going to be paying that expensive cost to run for those high memory loads for those durations that are 10 to 14 times higher versus some other languages. So I want to thank you. I hope I've been able to show you that pairing Rust with Lambda, it may be kind of an interesting use case, but at the same time, I do know from experience with customers that this is out in production. I've used it in production. I've used it in healthcare. I've seen it in some other places. If you pair these two together, you will get the beauty of all the things that are Rust, as well as all of the beauty and fun that is Lambda and that is serverless computing. And just for references, here's the sources from the presentation. So that's my blog at the top that's got everything on it. There's a project called serverlessrust.com, which has a bunch of examples and patterns of how to get started with serverless and Rust, focused around AWS. That is another really cool project. There is the repo that's got the entire API that we just walked through. Some of the AWS pieces, Cargo Lambda, and that QR code will connect you to all of my socials, as well as a really cool community called Believe in Serverless, where you can talk and chat with more serverless experts for free, because it's fun. So thank you so much.
Hands up for questions.
Alex, collage.
I have a couple of questions. So
Yeah,
we'll
sure.
go one at a time.
Yeah.
You focused on AWS quite a bit. Have you had experience with other cloud providers?
I have not used Rust with other cloud providers, but
In serverless.
yeah, in serverless, yeah, I've done a little work with Azure and a little bit of work with Google, but most of my focus has been in AWS. I've been out there for about.
What was your Azure experience?
My Azure experience was several years ago working with just functions and app service, and I've just started playing around a little bit with app containers, or container apps, sorry, because of the interesting nature of them.
And the second bit was the Cargo Lambda command.
Mm-hmm.
What does that actually do? Because you positioned it as it's a testing tool, but it seemed it generates some zip files. So what does it actually do?
It'll actually broker the compilation for you. So it'll sub out to Zig, and it'll build that Rust binary for you based on the architecture that you've specified, and then it allows you to run and test your stuff locally. So then pairing it with CDK gives me just this abstraction that I can specify, hey, here's my Rust project. Cargo Lambda goes out and deals with building and packaging and getting it ready to go for the Lambda runtime.
Okay, so this local test angle, it seems to deviate from the standard Rust testing tooling. Why is that happening?
It's because it's focused really around Lambda, because testing Lambdas from an integration standpoint is really focused around the event testing versus like the component level testing. So when you put your Lambda out, it's responding to these different JSON payloads. And so what their goal was to be able to give you a nice harness to be able to test against it. Because the only other way to do that is to kind of bolt into the serverless application models sandbox, and it gets a little bit clunky.
So it kind of instruments as if you were in the cloud environment
Yes.
with the events, but
Yep.
in reality it just hits the
It's just local. It's just running the project locally and then executing the payload off through the handler that I showed you. Yeah. Oh, guy in the back.
For that.
You make writing Rust look way too easy, but at least when I write code, I make a lot of bugs. And I'm curious what debugging, like especially with Lambda, you know, you're going from one Lambda to another, and debugging can be even more cumbersome. So I'm curious if you have any tips on just complex debugging and profiling when you're running Rust on Lambda.
Yeah, good question. So a couple of different layers. So I have successfully, and there's some steps with Cargo Lambda that you can attach a debugger to it, right? So that I can run Cargo Lambda locally, that I can simulate that payload, and then I can attach to a debugger inside of my environment. I've tested that with VS Code and Vim, and it works really well. And there's some instructions on how to do that. The second way that debugging is kind of the old tried and true events and prints, right? And kind of going against some of that. The third way is that once I'm up in the cloud, it's probably going to be using AWS tooling paired with something like Datadog so that I can get a little bit more observability into my application, especially as I start to get some traffic against it. Good question.
I got some really interesting use cases with HTTP2. I'm not sure of the because like I still see Lambda doesn't support HTTP2 yet.
Mm-hmm.
But if I have a violation stream root request use cases, does Lambda runtime get involved?
I believe you can, and I'm not, this is not my area, I believe you can do it with API Gateway, perhaps, would be the way to go. And you might be able to then connect Rust up to API Gateway and handle that event. So it wouldn't be directly against Lambda, it would be through Gateway, and then Gateway would proxy into Lambda. Stop.
Okay, I think this might be our last question.
All right, cool. I'm going to hang around after, so you can totally ask me off screen.
As a person who's been working with Rust for a year as you are,
Uh-huh.
how hard would you say it would be to migrate a Java code base to Rust code base?
It's a really good question. I haven't thought about that. Depends on how big the Java code base. If you're using Lombok, lots of other kind of interesting dependencies that are in there.
Like a full Spring Boot project.
Yeah. So for me at this point, again, I find that as Carl mentioned earlier, like if you stay out of some of the pitfalls of the Rust language, I say pitfalls more like the challenging parts of it. I would think it would be pretty straightforward. But what I find critical is if I'm a lone Rust person in a world, if I've got 2 or 3 people that are doing it with me, I feel like we'll move quicker together, right? So if you've got good Java programmers that have a specific need to pivot and they're like, I want to pivot to Rust, if you went together, I think you'd have some success. If you tried to make a convincing case for a 20-year Java developer.
I think that your screen with Rust is quite a convincing case.
Yes, and then especially if you're running Lambda for Java, and especially if you were trying to pivot from a container-based world to a function-based world, Rust is going to stack up really nicely there.
It does.
Yeah.
Exactly my case.
Yeah.
Thank you so much.
You bet.